My name is Przemysław. I'm a founding engineer at Quesma, and I'm here to talk to you about the unspoken overhead of the inverted index, or maybe what also I like to call it like a very lightweight introduction to how the text data is actually made available for search in your applications. So I want to begin with a few questions just to make sure that we are all on the same page here. And first of all, can I ask you to raise your hands in case you actually heard of inverted index and know how it works? That's good. I was expecting that. And can I ask you to raise your hand if you heard of Lucene project, the Apache Lucene project? Okay, that's cool. So I actually had one slide in case no one heard of Apache Lucene. So basically, and we have folks arriving here, so I'm going to use that actually. So Apache Lucene is basically a Java-based library that sits behind many of the OpenSearch internals, and it's important to stress that because over the course of this presentation, I might refer to some of the data structures or some of the algorithms that OpenSearch happily uses but actually doesn't implement them. And in order to figure out how stuff works, you need to dig a little deeper to the actual Lucene level, so to speak. And also, just for you to, it's not a CS dictionary definition, by the way, it's just my way to explain stuff in a very basic words for those of you who don't know. Let's stick to that definition just for now, that let's treat inverted index as a data structure designed to efficiently search across a set of documents based on their content. So now we are all on the same page. And also, let me explain why actually it's called inverted. So in a typical forward indexing scenarios, like you can think of any key value store or like a hash map. In this example, we have a set of cities which we can very quickly access, like think of any list or like an array. And the cities are linked to some of their properties. Think of any hashtags in like a social media application. So in case here we have New York, which is iconic and vibrant. We have Berlin, which is diverse and vibrant. And each city, object, or document, in our case, we can use these words interchangeably, is linked to the property. So in HashMap or in any key value store, it's going to be very effective answering this question: what properties does given object have? Because we can quickly iterate over, for instance, a sorted array of, let's say, city names. We get to city of Paris. We can fetch the properties. But it's going to be very difficult to tell us, like, what are the cities which are vibrant, for instance. In this case, we would have to scan through all the cities one by one, filter those tags. It's not very effective. So here's the inversion. The inverted index fundamentally tries to answer a very different question. And the question here is, what are the objects which have a given property? So the thing that needs to be very quickly accessible is just a list of our properties. In this case, these hashtags. Now we can access the hashtag vibrant, and here we have direct way to the cities which are described by this property. So this is the whole inversion, and this is why it's actually where it's coming from. And we are going to use a very simple example. Let's say that we have like an e-commerce store and free documents, free products in our document collection. There's an ID, there's category, there's a product description, which is text. And how would we search for a floral dress, for instance? So, by the way, I'm father of a daughter, so there's a bias in my examples for all the time. And yeah, so very naive approach, as I said before, would be just to iterate over the product descriptions and find the matches within those descriptions. Maybe we could take an advantage of a product category, but still it's not going to be very effective. It actually won't scale very well beyond hundreds of thousands of documents, and that's the scale that we are looking at in this problem. So a better approach would be actually to build the inverted index for product descriptions. And this is one of the takeaway, that actually the inverted index is constructed per specific text field, per each text field in a document that we are about to search. So how does it look like, and how inverted index is being built? We stick to the same example. Right now, I just truncated it so that we only have the document IDs and descriptions. So we have bold red dress, stunning and elegant as an example. And this is, of course, only a short fragment of the inverted index. I haven't built it for this whole set of 3 documents, just to keep my example short. So we basically have 3 documents to index with numerical IDs 1, 2, and 3. And most importantly, we have, as I've mentioned before, a sorted list of terms. For now, you can think of term as a word in the document. We will get to that and expand this further. So on the left side, you can see the term ordinal. So again, these are sorted. And actually having the terms sorted carries very significant performance implications that we will talk about later. We have also count, so how many times did specific term appear in whole document collections, and postings lists. Postings lists are just lists of IDs in which specific document the term has appeared. So in this case, we have the term floral, and in document 2 and 3, there's clearly a word or term floral. So if we were to add one more document to this specific structure, let's say the ID is 7 and it's a red dress, we have to build another chunk of the inverted index for that specific field in a document. It's actually at the Lucene level, these whole chunks of inverted index are called segments. And these are immutable. They stay in memory. They are then flushed to a disk. So at the Lucene level, that's where actually these are managed. What needs to happen is that we need to merge those 2 index segments into one. And again, having the terms sorted actually gives us a great leverage here, because we can use this fact to our advantage and actually merge sort that. So merging 2 index segments becomes pretty fast operation, right? So we can see here the chunk of the segments after merging. By the way, if you have ever wondered why bulk insertions of documents are way more effective, one of the reasons behind it is actually that if we can bulk more documents in single segment, then the better it is to actually have less index segments to manage. So that's one of the reasons. And same goes, by the way, with updating document in place. Unfortunately, updating a single document in place carries very similar overhead to writing a document, because we need to build that one index segment and manage it yet again. So updating single documents are pretty similar in that way to adding a new document. So yeah, definitely it's not the best solution to handle rapidly changing data with properties that gets updated thousands times, and only the latest version of the update matters. So we need to pay more attention to the actual term here, because up to this point, we have actually used the word in the text document and term interchangeably. And that was okay, but not anymore, unfortunately. We have to go through process of text analysis. So before the text is turned into a terms in inverted index, there's a whole process of text analysis. So here, the sentence, "I'm walking in Memphis," got turned into following terms. I walk in Memphis. More or less, this is how it looks. But there's the whole component called analyzer in OpenSearch that actually handles that. Some of the things that it's responsible for is tokenizing, so dividing the text into a set of tokens. Token filtering. There's a specific set of tokens that might not carry any significance when it comes to search. In this case, like in English language, the word isn't any helpful, so why to keep it? There's also stemming, so reducing word to its root form. In this case, walking and walked becomes just walk in our inverted index. There's a good set of built-in analyzers in OpenSearch, like dedicated specific to English language, for instance. We can also have some ability to customize it. For instance, add some synonyms that will be helpful for further full-text searches. And there's a Analyze API, which you can use to actually check. In case you haven't heard of it, it's actually very convenient. You can see what the output tokens would be for a specific analyzer. So here in this example, you have the analyzer, which is default for OpenSearch. When you create a text field, the sentence stays the same, and you can see that there's like a list of 5 tokens. But there's also another analyzer that we can test our sentence. And yeah, here we have, basically you can, if you pay attention, you can see that there's a stamped verb, as I've said before, and also there's, from the word Memphis, there's letter S removed, probably because letter S is also can be added to some words in English, and that doesn't carry much of a significance. So yeah, we also have to remember that tokens are not yet terms, and these are not equal. So while we can refer to tokens and use the Analyze API and see what happens, the actual term in inverted index might be different, and there's a lot of processing happening there. So here's one of the examples. We still keep with the same sentence, and we use text analyzer, so standard one in the first index. In the second one, we are using the English analyzer, and we are indexing single, very simple text document with the same sentence that has been with us for the last, I don't know, 7 slides or something. So we are using the term vectors API, which is immensely useful when debugging stuff like that. So the term vectors API will help us figuring out what the actual terms will be. And in this case, you can see that in English analyzer, there's way less terms. And also, the tokens of I and M have been joined. By the way, I forgot to mention that all of the terms are lowercase. This is something that is probably worth mentioning. And this brings me to one of the very important points when analyzing why the data is taking so much of space and processing. So I like to call this questionable terms. And these are the terms that you index, and they tend to bloat your inverted index, but doesn't really carry any significance when it comes to search results or just accessing your data. And here's one of the problems with the inverted index, that as you've set your analyzer and it's already working and you are ingesting data, you now have no control over what's going to happen, including the index itself, but also you might see very different data coming through. And I would like to give you a short example of log ingestion. So probably majority of people out there tried ingesting the log data from their systems into OpenSearch. And beautiful, curated, precise log messages that tells you exactly what is happening in your system. And suddenly you have something like this. And that's OK. That's just a stack trace from the JVM application. We have a text field. It's indexed as a text field. Like, what could go wrong? Well, basically, how many terms you think it produced? Guess, Somebody's counting. Actually, 56, to be precise. And if we take a look at the outcome of this term computation, how many of these will ever get searched? What we could definitely search is something like that, the class name. We could full text search on the log message, but the rest of this stuff, I would doubt it. And of course, it's just my example. It's illustrative, so we all search for different data. We have different use cases, so that might not be the case in some applications. But yeah, I wanted to basically say that the more structure you can apply to your data, generally it's the better. And yeah, I haven't heard that when the whole document database revolution was happening. Everyone was just, yeah, ingest as much as you can. Like, schema doesn't even exist, and suddenly you wake up with like terabytes of data, and that's becoming a problem. I've seen a few, maybe that's my biased perception here, but I've seen few people smiling, so I guess I'm not alone, and someone may also relate to that. So the question is, how can we do better in such cases? And there's first thing that comes to my mind is to try putting some structure over our data. Because if we do that, dissecting some of the properties will give us at least something to work on with improving how we handle our smaller chunks of the data. One of the options is not to index data at all. It's actually possible in OpenSearch. I know it's a very trivial example, but believe me that it's not very uncommon to witness, especially when the default option is to index the data. So you can save a lot of space and save a lot of power that would be wasted on processing the ingested traffic. If you think of any data that won't be full text search or some kind of metadata that's just carried through, this is definitely one of the options that we can use. And some of you may have noticed that the class name in my previous example was of type text, and that's not appropriate. At least in this specific case, there are better ways to handle that. And the keyword field type is a very good example for this. So this is a separate type used in OpenSearch for text data, which basically tells skip the whole text analysis process and index this whole text as is. So essentially, the entire field becomes a single term in the inverted index. If you think of any structured data, like, for instance, zip codes or ID or emails, this can even get harmed from very meaningless tokenization. So it may just not make much sense to actually use full text field for things like that. Also, keyword field types enable segregations. And here you can see how it works using the term vectors API again. So we have our updated data structure. We have our log message being ingested. And we are using, again, the term vectors API. By the way, there's a lot of options here that you can set to see what is happening. And yeah, you can see there's one single term with some metadata. By the way, all the examples are coming from OpenSearch Dashboard's Dev Console, which is a very handy tool. So if you don't know it, it's quite fun to use an API with it. And yeah, we cannot, however, if you remember when I said about enabling aggregations via keywords, we cannot have this discussion finished without mentioning doc values. Doc values are actually a property of keyword field type. By default, it's enabled, so you might not notice that this even exists. Doc values are designed to enable sorting and aggregations, but the cost is actually introducing a totally separate sort of columnar, like document to value style of data structure, which is additionally built at the indexing time. So that's the cost that you have to pay. However, you can also disable that. And if you think of keywords which are not used for sorting or for aggregation, that's the way to go. One of the things that comes to my mind is, again, this is my illustrative example. This might not be the case for some of you, but if you think of log level, like how often do we aggregate over it? Usually, in most cases, at least from my experience, log level is super useful for filtering. Like, okay, let's see all the warnings. Let's get rid of debug messages. But if we are in a highly distributed system, which just keeps spamming our log, the percentage of log levels being warning or something like that may not be the most valuable metrics. So class name, again, if we don't plan to do any aggregations on it, we can also disable that. So here's the layout of our improved structure. My intention here is basically just to build kind of intuition and show you what actually needs to happen under the hood so that you can search data the way you search. And also a quick step back into the inverted index. What if I told you that the inverted index actually stores even more data than on the examples that I had before? Well, and I mean like a data related to specific terms, so purely like a part of the inverted index, logical data. If you ever paid attention to the specific index options property of the text field type, you have noticed that there are 3 available options. Here you have docs, frequencies, and positions. This is actually quite surprising because the positions, which is the worst option disk space-wise, is actually our default. So in this option, we store the document number, obviously, the frequencies, and also we store the term position. Now, you might ask, like, why the most expensive option is default? Well, that's because it's useful for some specific types of queries. Like, have you heard of span queries in OpenSearch? Yeah, these are very rarely used, but they tend to happen. These are queries that are related to position or like precedence of terms. So we need to have that information. And here, again, the term vectors API, it actually can show you that, well, yeah, we not only have information about token like frequency, but also where it starts, where it ends. So there are some queries that use that information. However, again, it's most costful option storage-wise because we have to store that data. So there is another field type which is called match-only text. And this is that space-optimized text field type variant. You can think of it as standard text field, but with the index options set to docs. So it's almost the same as a text field, but with few limitations. So let's see what we actually gain and what we lose when using that. All the relevance calculations cannot take place because basically we do not have any frequency counts, so we cannot really compute the relevance according to the algorithm that is used. So we also do not store any term positions or frequencies here, which is, in this case, our main selling point of that field type, because we save space on the index size. As I've mentioned before, some of the query types are not yet well, they are not supported, and they won't be because it's impossible to get that data. So, and yeah, if you haven't heard of these query types, most likely you won't be using them. So why not to use this specific field type? So just a short recap. We've learned about what an inverted index is and some of its mechanics. We took a closer look into some of its internals. And we've discussed few options how to index our data in a more efficient way. And also, hopefully, we've built some intuition about what additionally is done inside OpenSearch so that your data is available to, fast search. Yeah. That's it from me. Thank you all.
We have time for questions.
Okay.
Any questions?
Let's do questions.
I have a question. Putting all of your proposals together, I can speak. Okay, let me try that again. Okay, yeah. Putting all of your proposals together for a typical logging use case, how much of a optimization would you expect, like especially on the memory profile?
On the memory profile, well, I would rather expect. If we talk about disabling those specific functions that I've mentioned, I'm not sure what would be the actual gain, because the problem here with assessing that is that the real data sizes are very different. So, for instance, in case of let's say that we were to disable the term frequencies like storing, that's probably just few bits. But in case you're having longer terms, then the percentage would be, not that significant. So I've seen few benchmarks online by people who done that. So just to give you an example, in many cases, match-only text field gave people a 10% storage gain. So it's not like order of magnitude, but again, this is storage gain. You've mentioned memory. That's even harder to assess, actually, because of just different types of data and different sizes of terms. It's actually quite hard to assess that at this point. So I guess there's not a common answer for this question. I'm sorry.
Okay, we'll try it out then.
Do you know, are there any tools or automatic ways that would suggest these optimizations for you? Like, for example, you're never using span queries, so maybe you should just disable that and save some index time.
That's a good. Oh, yeah, it works. That's a very decent feature request for OpenSearch, I guess. I haven't heard of any. So, yeah, luckily we have community and presentation that will get people up to speed with some knowledge, but yeah, unfortunately, I don't know any tools that will suggest you that. Also, it's quite difficult to suggest some of the things that I've mentioned up front when you actually, don't have yet your data, or you're talking about existing data sets, right? Yeah, that's quite hard. That's quite hard to do. Unfortunately, I don't know any products that will give you these answers.
Not a question, more a comment. A configuration with wizard is a good idea for a computing contribution.
Any other questions?
So match-only text, you said, gives about a 10% storage improvement. But I think from the performance side, it gives you much more significant gains. Is that right?
I agree, yeah.
And
but just to clarify, this is just one of the benchmarks I've seen online. So I don't have any universal way to tell how huge this gain will be in specific case, unfortunately.
Yeah, from the user perspective, it basically disables scoring and relevance ranking. So I think the user has to decide whether they want to do that upfront, because I don't think they can add it later on. So do you have any guidelines or heuristics for users to make that choice when they decide upon the mapping?
Yeah, I mean, to some extent, it might be pretty simple to decide if you are actually interested in ranking at all with your queries. Because fundamentally, I would say that if we design some kind of a system and lay out all the questions that we have, like all the problems that it has to answer, and all the cases that we will access our data, it should become very natural to say if we are using if we need the relevance or not. So I would say that not much of a heuristics, but rather just figuring this out based on the usage pattern for our data. That's probably the best thing I could suggest at this point. Thank you.